Today I'm going to talk about graphing functions using derivatives. Keywords will be X-Intercepts, first derivative use, decreasing, increasing, critical points, second derivative, concave up, concave down, and inflection points. Going a little bit fast because there is no need to slow down here and explain everything. Just like an idea about the content. Here we go. Graphing functions using derivatives. First example, f of x equals x minus 3 times x plus 3 to the second. It's in factored form, which is a good use. It's helpful to start with that. This way I could take advantage and find the x-intercept. Here we go. So if you set f of x equals 0, you get x equals negative 3 and 3. You could see that. This will give you negative 3 and this will give you 3. But I wrote them in the right order. We kind of like write them, 1, 5, not 5, 1. Same idea, negative 3, then 3. Those are called x-intercepts. If you could do it, do it. If it's too hard, it's fine. Usually when we graph by hand, we do the best that we can and identify concavity, increasing, decreasing, and we'll move on. But it doesn't hurt when you have this to do the x-intercepts first. My second step is finding the first derivative and setting it equal to 0. But because this video is not about how to find the first derivative and how to apply the product rule, which I have it covered in different video, I could skip all the steps, but to benefit you, if you want to practice yourself, I displayed them all for you. So that's what I mean. I don't want to go slow and write or read every single step. If you need it, it's right there. You could pause the video anytime by hitting the space bar, as you know. Now, finding the derivative using the product rule, setting equal to 0, you'll end up with 1 and negative 3, or negative 3 and 1. What's the benefit of setting the first derivative to 0? This is the benefit. You make a line, you call it f prime sign. At negative 3, we call it critical point. At 1, we call it critical point. We're going to cross the x-axis at if f prime is graphed. F prime will be valid at negative 3 to be 0 and at 1 to be 0. So if you want to graph f prime, you're going to cross the x-axis here and here. That means when you cross here and here, between them, either you're all the time above the x-axis or all the time below. In this case, it's all the time below. Plug in any number for the convenience between negative 3 and 1. If it's negative, mark it as negative. To the right, I have the answers for you, positive here and positive here. For the convenience, you could just plug in 2 in this right here. Let's just quickly test it. That's positive. 2 is convenient. You could plug in 5. 2 minus 1, positive. 2 plus 3 times 3. The whole thing is positive. We don't care about how much, but that's positive. And that's how you test it. So we have enough ideas so far, but let's take advantage and move on. Second derivative. After you have the first derivative, do the product rule again. You end up with the second derivative. Factor 6 out, set it equal to 0, you get x equals negative 1. We don't know if it's an inflection point. It's a potential inflection point. It's a candidate to be an inflection point, what we don't know yet. Now, at x equals negative 1, it came up to be an inflection point because f double prime is 0, and when you test the numbers on the left, it became negative, concave down. When you test the numbers on the right, plug in anything above negative 1, like 0, for example. Let's take a look. 0 plus 1, 1 times 6, positive, yes. Concave up. If it changes concavity about this point, we call it inflection point. What do I mean by this? I tried to put the graphs, as you could see, 0 right here, 1, negative 3. Even with my graph, look, this is 0. Actually, it's a little bit off. Oh, no, it is actually. It is. This is negative 1. This is 0. this is 1 right here, and this is -3 right here. So it's kind of hard to make lines and make it all busy, but they're aligned. Let's take a look. Here it says to the left of -3 you are increasing. Yes, to the left of -3 you are increasing. Between -3 and 1 you are decreasing. You're going down. After 1 you are increasing. After 1 you are increasing. Good. Here we said x-intercept -3 and 3, x-intercept -3 and 3. Second derivative says to the left of -1 you are concave down. To the left of -1 you are concave down. To the right of -1 you are concave up. Local minimum, that's local minimum. Local maximum, increasing, decreasing, and concavity also supports that right there. Now how to find the values right here? Just plug them in. Here 1 local minimum, just plug in 1 in this and you end up with -32. That's how you do it, nothing much. Okay, let's take more examples. X cubed minus 6x to the second plus 9x. This is f of x. I factored x out. Then this gets factored to x minus 3 to the second. Set it equal to 0 to look for the zeros or where the graph crosses the x-axis. I get 0 and 3. 0 from here, 3 from here. Okay, let's go after f prime. If this is f, this is f prime. 3 goes down, this becomes second. 3x to the second, 9x becomes 9, and so on. Factor 3 out. This gets factored to x minus 3 and x minus 1. So I get the 1 and the 3 as critical points after you set f prime equal to 0. Now we take advantage of this and we make a number line with f prime as a title. Test it to the left and test it between and test it to the right. Increasing, decreasing, increasing. That means we have a local max here. We have a local min right here. Let's go after f double prime and find out concavity. F double prime, the derivative of the first derivative, that's going to be 2 comes down, makes it 6x. Minus 12x is minus 12, and this will go away. Set it equal to 0. With simple algebra, you get x equals 2. At 2, we have 0. Inflection point, yes, because concavity changes from going down to going up. Test it with numbers. You will see that this is positive, concave up. Negative means for the second derivative that the graph of f is concave down. I'm using black to refer to f. I'm using blue to refer to f double prime sign. Alright, one more time. Trying to align them. This is 1, this is 3, so somewhere is 2. Here's my graph. This is 2. As you can see, I'm doing my best to align it. And here's 1 and here's 3. Increasing, decreasing, increasing, increasing, decreasing, increasing. Inflection point at 2. Concave up to the right, concave down to the left. How much you get this as 4? Just plug in 1. It's a critical point, and we know it's max. Just plug it in. Plug it in right here. These are x-intercept 0 and 3, 0 and 3. Plug in 3 here, you get 0 also. So it's on the x-axis, right? It doesn't go below. Let's take another example. This time it's going to be to the 4th, not to the 3rd degree. X to the 4th minus 6x to the 2nd. This is a 4th degree one, not a 3rd degree. Factor out x to the 2nd. We get x to the 2nd minus 6. This is considered to be a difference between two squares. You might wonder, like, why 6 is being considered a square? Well, it is a square of square root of 6, as you can see. Set this equal to 0 to look for the x-intercepts. I get 3 zeros, one from here, one from here, one from here. Those are called x-intercepts. We go after f prime. Derivative of this would be 4x cubed minus 12x. Factor 4 and 1x out. This still a difference between two squares. And that will give you minus square root of 3 and square root of 3. So I do have 3 critical points. And the number line with title f prime will look like this. I'm saving you some time because of the concept. I don't need to waste your time showing you what I'm plugging in numbers and how to factor this, because it's similar to this. So anyway, we have a minus, plus, minus, plus, just by plugging in some numbers from here for the convenience in the f prime and see if it's possible negative. Negative for f prime means decreasing. That's my original function. Positive means f is increasing, negative means f is decreasing, and positive means f is increasing. Which means we have a local minimum here. Increasing, decreasing, we have a local maximum. Decreasing, increasing, we have a local minimum. Let's go after f double prime. We know how to find the derivative of the derivative and call it second derivative. Factor 12 out. This is still difference between two squares, which gives you x minus 1 times x plus 1. So I have 3 points as zeros for f double prime. They could be inflection points, but we cannot tell. We have to test it. It comes up to be like at 1 and at -1 inflection points, but not at 0. Why? Concave up, because f double prime is positive to the left of -1. Concave down, then concave down again, and now concave up. When it changes concavity, we call it inflection point. Here it did not change, we don't call it inflection point. Let me align a graph with this and support. This is square root of 6, and this is square root of 3 right there. 0, negative square root of 3, and square root of 6 for the x-intercepts from here. At -1, I have -1. At 1, and I have 1. This guy here tells me that it's decreasing, increasing, decreasing, increasing. Yes, decreasing, increasing, decreasing, increasing. Here, f double prime tells me concave up to the left of -1. Here's -1. Concave up to the left of -1. From -1 to 0, it's concave down. Also from 0 to 1, it's concave down. Then after 1, it's concave up. So we do have an inflection point here. We do have an inflection point here because concavity changes from up to down, and here from down to up. Now, since you know that this is local minimum and this is local minimum and this is local maximum, just plug in the numbers in f of x and you will find the exact values, so you could be able to graph it with more detail. That should do it for this video, and I'll see you in the next one. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.